Good evening. Thank you for joining us tonight for the final instalment in this term's science series lectures. Tonight, Dr. Patterson will take an engineering look at the physics of time travel and how to build a Tardis. For his master's thesis, Dr. Patterson did a review of the application of quantum mechanics to cosmology. His plasma physics PhD was more practical, focusing on experimental investigations into the operation of a Kaufman-type ion thruster. He then worked as a postdoc on a top-secret feasibility study for a novel concept weapons design. After his viva, he was offered a job on another top-secret weapons project, for which the security clearance took 7 months to process, only to be declined because he had recently acquired an Irish passport. That twist of fate eventually led him to finding his way into secondary school teaching and joining the engineering department at St. Paul's School in 2010. There will be a chance for questions at the end of the talk, so please do use the Q&A function at the bottom of your screens, and I'll now hand you over to Dr. Patterson.
Good evening. Hopefully you all can hear me. Who doesn't love time travel? So I'm going to look at some of the physics of time travel. My interest was raised when I was quite a young teenager. Had some strange experiences where, like deja vu, and I think a lot of people do have that kind of thing, and the ideas of time travel and what you could do. Maybe you could go back and change something, maybe relive the perfect day, and just the storytelling structure of time travel movies are really rich in how to explore those human feelings in a kind of sci-fi way. But a lot of people take those ideas into studying the real world and studying physics, and the ideas of is time travel actually possible have pursued a lot of physicists, because there's loads of papers on there on thoughts about the strangeness of time. It's one of the big mysteries. So here we go. Let's start. Is that working? Yes. Okay, so the TARDIS. Doctor Who's TARDIS stands for time and relative dimension in space. But you see this acronym appear in research papers. So here's one I came across. Whoops. Traversable acausal retrograde domains in space-time. Paper they present geometry which is designed to fit a layperson's description of a time machine, a box which allows those within it to travel backwards and forwards through time and space as interpreted by an external observer. Time-like observers travel in the interior of a bubble of geometry which moves along circular acausal trajectories through space-time. So cause doesn't follow effect in the normal flow of time, but there will be loops, closed time-like loops, CTCs. So a certain time-like observer inside the bubble can maintain just their normal reality, persistent acceleration, and their world lines can close on. So there are multiple examples of this through physics literature. Here's one of the examples from a Popular Science article. So colliding gravitational waves from accelerated protons rip a wormhole in space-time, and then with some kind of negative energy, dark energy, you keep this wormhole open and you stretch it up, and maybe to the size that a person could go through. Typically, if you've got a wormhole, then you can, each end of the wormhole, if it's separated in space, could potentially travel at a different rate in time. So a typical scheme would be for one end of the wormhole to be close to a large gravitational mass. And general relativity tells us that time goes slower near a large gravitational mass. So one end of the wormhole would be slowed down, the other one would be at normal rate of time, but they would still be connected instantaneously. So effectively, if you wait long enough, then you go in the outside wormhole, you would pop out back in time effectively. So first thing we need to ask, is this even logically consistent? So you could imagine you've got your two spatially separated wormholes. What happens if you go in to one? So this is time moving from the left of your screen to the right. So at some point you hit the wormhole, I can go back in time, but I come out before I went into the wormhole, and I could collide with myself at this U event, and then it would cause a paradox. If I knocked myself out of that trajectory, I wouldn't have then gone into the time hole to be able to come out. I mean, there are other paths, so I could imagine going in at a future point, and then coming round and missing myself, and then it would be logically consistent. You could imagine a simplified deterministic system. This is Conway's game of life, where the rules are just a very simplified cause and effect. So for each block, there's simple rules. If you've got one nearest neighbor, the next time your square is white, you can imagine these little creatures. If they've got not enough nearest neighbors, they die. So this little black square turns white if it's only got one nearest neighbor. If it's got two, it'll stay as it is. And if it's got three nearest neighbors, it will reproduce. So if it's a white square and it's got three, it will turn black. And if it's got more than that, then if it's black, it'll die and it won't reproduce. So here we have, moving from left to right, we've got the three on the right-hand side turning black, the two ones, the three at the top turning black, and the two black threes and the black two staying the same. And you have an evolution in time. With the evolution in time for this shape, it's called the glider. After 4 time steps, it looks exactly the same as it did at time step 0, but it's shifted one square to the left and one square down, and it evolves. But you can imagine a system where this has retrocausal effect. So you've got time travel happening. So one of the squares in the future goes back in time and knocks out one of the squares. It's a bit like a mini grandfather paradox in this system. Randall Munro, cartoonist, illustrates the grandfather paradox like this. It's quite good. So someone travels back in time, says you're about to have an idea for a time machine, doesn't know this before the doc hits the toilet with his head and knocks it out of his head, can't think of the time travel. And you could imagine that there's some kind of chronology protection system that stops time travel happening, stops this weirdness happening, and this so you don't get these paradoxes. And Stephen Hawking famously suggested this time chronology protection. There's some kind of law of physics that would stop this happening, but not everyone's convinced that it's impossible, that it would create contradictions. You can imagine our little Conway's Better Than Life, or Conway's life model. So if you had an external observer looking at all the different options with time travel affecting the past, retrocausality, that observer could select which ones were consistent and program them in, and it would be perfectly consistent to have that system that could cause it back if you just weed out the ones that are inconsistent. David Deutsch has suggested this is what quantum mechanics does. If you bring the idea of quantum mechanics into the idea of time travel, so instead of it being inconsistent, you would perhaps pop back into the multiverse, or if you pop back with this, the same, if it's probabilistic, then you would have basically a quantum interference that would stop these inconsistent timelines occurring. So you could have a multiverse solution that you've got multiple consistent ones, and the dynamic one, like in Back to the Future, you would have things maybe fade away and just the consistent ones left. There's other ideas of maybe there's another dimension in time, so you could imagine the whole universe evolving in a separate direction of time and ending up on a consistent level, perhaps like a fixed timeline where everything is consistent, where the future is consistent with the past. Similar to, so all these inconsistencies could just fade out. Similar to how things settle to a low energy state in a quantum system. So if you've got something with many different quantum possibilities, and you let it settle, there's a process called quantum annealing, where the system will solve this and find the lowest energy state. So you could imagine with the whole block universe kind of evolving in this separate time dimension and ending up in this self-consistent state. This idea appeals to me as that you can almost imagine seeing under the bonnet of the multi-worlds interpretation, that there's a consistent history that is hidden, but and the Broglie-Bohm interpretation of the pilot wave interpretation has that built into it, so that there is this uniquely consistent history that's deterministic with everything that happens, that seems to have these effects, non-local effects or retrocausal effects that move the particles about to make things consistent. Okay, so having looked at whether it's logically possible, it seems to be. There's papers in philosophy, papers in physics suggesting that yes, there are consistent ways to do time travel. Part of the problem with these papers is often you need some type of exotic matter. Sabine Hossenfelder has done a great video on warp drive. There's a paper released recently about the possibility of warp drives without exotic matter. There's been a theory for warp drives around for quite some time called the Alcubierre drive. Hope I'm saying that right. But it relies on exotic matter, and we haven't seen any. But there are other ways to distort space-time using real matter. So what these theories with time travel or with warp drive typically do is they solve Einstein's fields equations. So on the left-hand side, we've got the stuff that refers to the geometry of space-time. On the right-hand side, it's the matter. So let's look at this a little more detail. So we've got two curvature terms. The metric tensor, which is the description of the background space-time. Added in here is the cosmological constant. Einstein's biggest mistake, although it turns out it wasn't. And then on the right-hand side, we've got the stress energy tensor, which has all the matter fields, all the energy fields, pressure. And if you solve for a specific geometry on the left, you can predict what type of matter arrangement would cause that. But typically these time travel systems require exotic matter that we haven't seen. So no exotic matter, can we still do it, is the question. So with real matter, there is this time symmetry built in. So this is a Feynman diagram of an interaction with an electron and a photon. So it could be just a photon changing direction with or electron changing direction with an interaction with a photon. So you've got time evolving as it goes up the screen, and movement in space plotted on the horizontal axis. We've got so the electron's moving to the right in space, and then it has an interaction with the photon and starts moving to the left. And the laws of physics of particle physics are completely symmetric. So this can be rotated in space and time. So here's two electrons interacting with the exchange of a photon. So you've got two like charges repelling. But what you can do is rotate it even further. Here we've got an electron and a positron approaching each other and creating a photon. Now, the physics of that interaction is exactly the same as the one that's been rotated. So you can imagine this positron as being an electron that's actually going backwards through time. The completely consistent physics. And this idea has been used in recent movie, Tenet, of inverting matter as a time travel mechanism. So you've got matter going forward in time and matter going backwards in time in this movie. And you've got the time machine who's got two rooms. Room A, the forward in time traveling matter goes in and it comes out in room B. So there's the time machine floor plan. So you start on the red side, decide you want to go back in time. Let's say you enter the time machine at 10:30. The machine inverts your matter. You're now traveling backwards through time. You exit the machine in the blue side. So time has been reversed for you. Everything around you is rewinding. Clocks are ticking backwards. You're going backwards in time. You look over to the red room and you'll see yourself going into the red room as you're coming out of the blue. And you'll go backwards in time. At some some point when you've gone far enough back in time, you decide you want to go forward in time again, and you enter the machine on the blue side before you exited because you're going backwards in time, and then you re-emerge on the red side. Normal time flow has been restored, and you've traveled back in time 30 minutes. And Tenet has great fun mapping these intersecting timelines and trying to make them consistent. So from the outside, what you would see, so on the inside, sorry, on the inside, you would drive in on the red side, you see the blue car, and that's going to be you in a few seconds. And then both cars get to the machine, it activates, and then as far as you're concerned, you drive out on the blue side. But as far as everyone else is concerned, you've vanished from existence as you've gone into the red machine, and the blue version has gone into the blue side and has completely vanished. Okay, so could we build our TARDIS like this, somehow invert its matter to be going backwards in time? Slight problem with this is that there's an equivalence, there's a very famous equivalence of matter and energy in physics, but also of matter, energy, and information. All the information that is in that in a particle or any physical system or radiation has to go on. It can't be destroyed. Information can't be created or destroyed. So looking back at our electron going into the time travel machine, meeting the positron, they would annihilate, and all that information about their existence would be in the photons that are created from that explosion. Effectively, you have matter and antimatter coming together and turning into pure energy. And to do the reverse process, you would need that amount of pure energy that's in that matter to create those forward going electron and backwards going electron, the positron, out of nothing. So maybe the time machine would look a bit more like this. You've got positive matter suddenly disappearing in a ball of energy. Although if you do the calculations, it's going to be a little bit more energy than this. Okay, so this is the Tsar nuclear bomb, which is the largest nuclear bomb that was ever exploded on the planet. It turned the equivalent of about 1 kilogram of antimatter and 1 kilogram of matter. So about 2 kilograms of matter turned into pure energy. If you look at that, the scale of other nuclear bombs, it dwarfs them all. So just for a kilogram of matter changing direction in time, you're talking about a crater most of the way between Manchester and London, and a destruction over quite a large area beyond that. Okay, so is there a way around this? Is it, and interestingly, there does seem to be circumstances where information travels non-locally without the need for photons. And recent work on black holes seems to suggest this is what's happening with Hawking radiation. So there used to be a divide between the physics community about whether information was lost in black holes forever or whether it escaped. Particle physicists tended to say, okay, laws of quantum mechanics say that quantum information is never lost, so it can't possibly be lost. There must be something going on. General relativists or theorists like Stephen Hawking, he claimed that yes, information goes in and it doesn't come out. I think he famously made a bet about this, which he eventually conceded, that before he died, he believed that information did escape from a black hole. And his work on Hawking radiation was one of the things that started that, or started resolving that information paradox. In his scheme, the gravitational field is so strong on the boundary of this black hole that within quantum mechanics, the laws of quantum mechanics, you've got the possibility for the uncertainty principle allows for the possibility of creation of these virtual pairs. As long as they don't last for too long, they annihilate. They won't violate the laws of quantum mechanics. But if the gravitational field is so strong on the boundary, it can stretch these virtual particles apart so that they survive. You can imagine this as a little consistent loop of time travel. So you've got an electron going forward in time and borrowing energy from the uncertainty principle, and then being knocked back in time with the positron and cancelling itself out. So little tiny consistent loops in these foaming space-time. And then at the edge of the black hole, you have these stretched apart. Now, Hawking initially thought this would just be like a completely random radiation with no information about what fell into the black hole. But further work on black holes, in fact, recent work on black holes, is tilting the theorist community towards believing that somehow the information does escape. So these two particles could be, they're created entangled, and there's some kind of connection still between them where information is shared between the internal workings of the black hole and the radiation and matter that escapes out of the black hole. This is sometimes framed as the principle of complementarity. So what goes on inside the black hole maps onto its two-dimensional outside surface. It's the holographic principle. So in 1997, Maldacena conjecture using string theory showed that in these contexts holography is true. So it's like a separate simple model. Well, not simple. It's a mapping of the physics of black holes onto a space where we can analyze the boundary. And in these systems, it was shown that all the quantum physics on the outside surface related to all the physics in the volume perfectly. And if information wasn't lost on the surface, then it couldn't be lost in the dynamics of the black hole that were in the body. I'll post references to this because this bit is beyond me, but it started off in string theory, but later work has suggested that it's not, you don't need string theory for this. It's consistent with just a layer of quantum mechanics on the background of a general relativistic description of black holes. So this is what it looks like for the information in a black hole. So at a point which called the page time, information starts to leak out of the black hole. So Hawking's initial entropy calculation suggested that the entropy of a black hole always increases. But at some point in an evaporating black hole, it hits this maximal information content about halfway through its evaporation time, and then information starts streaming out of this black hole. It's almost like an inversion. It becomes more and more like the description of a white hole towards the end of its life, until it evaporates in an extreme burst of energy. There's other theories exploring the link between the inside of a black hole and the outside. One is the ER equals EPR conjecture. It's not an equation like a normal equation. It refers to two different theories. One's an Einstein-Rosen bridge, which is the wormhole. And on the other side, you've got Einstein, Podolsky-Rosen, and their spooky action at a distance paradox paper, which was shown to actually be true in physics. So you have this entanglement of separated particles. And this suggestion was that the physics of wormholes was actually very related to the physics of entanglement. In some way, particles and black holes are on a continuum, and the connection between entangled particles acts, it's like a wormhole connection. So if you got your classical wormhole held open by the exotic matter, the new wormhole is the inside of the black hole is connected via this quantum entanglement with the Hawking radiation, and the information leaks out. It's like it gets there without having to be sent by a signal, by a photon arriving, but it just appears in the statistics of what happens to the random quantum particles. That information appears on the outside of the hole. I've got a link to a video of Seth Lloyd talking about this. Is really good on my YouTube. I'll share it hopefully with you when we share this video, talking about this mechanism, the Horowitz Maldacena mechanism, and he did an extension on that, and it's a really robust system where the information does escape. You've got some kind of non-local transfer of information. But if you have non-local transfer of information, then you've got information that has effectively traveled in time, and you get so the conclusions seem to be backing up the possibility of these effects traveling through time. Oops. Let me go. There's other possibilities that about the release of information. This one I like particularly because it uses the Broglie-Bohm pilot wave formulation of mechanics, where information can be transferred non-locally through the pilot wave. So the pilot wave has non-local hidden variables that refer to across all time and space. So this could describe how that information appears outside the black hole as well. Okay, and something like this was described in Interstellar. So here's their model of a black hole. So the black hole has got a circular disk of accretion material that underneath you see the light of the back of the accretion disk that's kind of been bent round. So it looks like a disk underneath, and the same at the top. This is a quote from their movies. Just so they weren't looking at inverted matter, but the possibility of time information traveling through time. So time is relative, it can be squeezed and stretched, but it can't run backwards. So that was the limits on that movie. Matter couldn't travel backwards through time. The only thing that can move across dimensions like time is gravity. And so all this information that's gone into the black hole in the movie was somehow linked to the outside world and could leak out and affect and cause ripples that then changed the future in a consistent way. So this is consistent with the laws of physics. It's a consistent time travel idea that would be consistent with the laws of physics. Okay, so with a time travel machine, you can only go back as far in time as the time travel machine existed in physics. And so to build our Tardis, we would need to go back as far as we could. We would need something existing as a black hole right from the beginning of the universe, a primordial black hole. And there's been a lot of recent work on detecting black holes. If you asked about how many primordial black holes were around up until 2019, you would have been told that it's a low possibility, but recent research has opened this possibility up, and there may actually be millions of these black holes out there, and they still haven't been found yet. So there's gaps in the data that haven't been detected yet. So there's possibility for supermassive primordial black holes, and also black holes more the size of the planet or asteroid size, and they would have to be primordial black holes, because a black hole the size of a planet can't be created by a star. You need a lot more matter to create a black hole with a collapsing star. So if we find small black holes, then we would know that they're primordial black holes. This is a recent paper on the possibility that these primordial black holes are dark matter. So at the minute, dark matter is a mystery. So of the normal matter that of the matter that we can see, including what we can't see, or of the matter that we measure in the universe gravitationally, we see the effects of. About 80% is dark matter, and about 20% is the normal matter that we can see. And the windows for these primordial black holes that could still be out there, yeah, there's enough possible black holes that we could discover that could explain a large fraction of the dark matter in existence, possibly even all of it, although there's likely other forms of dark matter. So if we look at that plot in more detail, so this is the areas that have been ruled out by studies. So different studies have ruled out different the existence of different black holes. So for instance, on the left-hand side down here, these black holes are too small to be in existence now, this long after the universe, because they would have evaporated already. But primordial black holes of about the size of an asteroid or larger, up to maybe planet size, could easily fit in this window that we haven't been able to detect, either through microlensing events or through LIGO measurements. And if you look, this is this potential fraction of the dark matter that could be primordial black holes. So you could have all the dark matter be these small black holes, or even really supermassive ones from the beginning of time. Whoops. And okay. So the space out there could be teeming with these primordial black holes. Next question is, could we find one potentially close enough to get to without having to have our exotic matter to get our warp drive across the galaxy again? And the answer is a tantalizing maybe. If you look at recent studies on Planet X, there's a proposal that it could be a primordial black hole somewhere out beyond the planets. There could be a tennis ball size black hole, about 5 times the mass of the Earth. That would be the explanation for why there are some peculiar orbits of other objects in the outer solar system. So we take our primordial black hole in our outer solar system, and we build a quantum computer, or Tardis, that can model the black hole, and then we can send information into this black hole that could eventually pop out connected to as the black hole was created. And if we've got a primordial black hole, that could be information coming out right at the beginning of time. This stage, I have to show this off. This is how do you do that? This was created by my brother for the talk. This is fantastic. So I want to give a shout out to his crafting YouTube site, Nat1 Videos. So imagine there's my quantum computer that can model a black hole, and I can send information back through this non-local connection inside of the black hole. So my black holes inside the Tardis. Let's get back to the slides. Okay. Smaller than the outside, than the inside. So you've got a universe of information on the inside, and quantum computer. And in reality, it would look more like a Dyson sphere. So if we go out to this primordial black hole in our outer solar system, we could have this Dyson sphere and measure all the information coming out and feed information in. Okay, so will we actually do it? If you create a time machine, when we do it is kind of irrelevant. The question is, has it been done? I mean, are we living in this universe that is consistent with time travel? There's a interesting idea that Wheeler came up with in a conversation with Feynman on the phone about the idea of why all electrons are identical. So what if it's all the same electron? What if this electron is just zipping backwards and forwards through time? And that's why all electrons look the same. So you've got bits of this Tardis multiplied in all these timelines that actually have created all matter. And Feynman took that idea further and got a Nobel Prize out of his work on some of that. So we've flipped things on the head, so that the universe itself could be created by this exploding Tardis. Everyone has a favorite Doctor Who. Matt Smith's Doctor is my favorite by far. This sequence where you've got the exploding Tardis that recreates the universe. So he's looking at Tardis, and then you've got the Pandorica, which takes this information of our universe into the exploding Tardis. Doctor drives this like quantum computer with the information about what's in the universe back into the exploding Tardis to rebuild the universe in Big Bang 2. So you have this story describing this idea of the cycle of matter going back and creating the universe. One other problem that we'll look at, so this infinite regress creating all the matter, you would have an equal amount of antimatter going backwards in time through these primordial black holes as you would have normal matter going forwards from the beginning of time. And the question is, why would that antimatter from the primordial black holes end up in black holes when the rest of the matter didn't? It created the universe on a big scale. And the answer to that, well, my suggested answer to that question, I came across this paper. So actually before that, so the idea is like you have this loop, like feedback loop. So if you switch on your time machine, you can imagine that if something's going into it before and then coming out of it, you would create like a feedback loop, like holding a a microphone up to a speaker, you get this massive feedback loop, which would create a big bang. Okay, so this idea about why why we don't see the antimatter and how it could end up in these primordial black holes was suggested to me by a paper of Wheeler's. Where is it? So in 1957, John Wheeler and Charles Meissner wrote this paper about classical physics as geometry and looked at the possibility of particles being mini wormholes. So the pure geometry, so the electron would be one mouth of the wormhole, and the positron would be the other mouth of the wormhole, and it's just described, you would have the wormhole holding on to the electric field, going in one end and out the other, just perfectly described by geometry. Let me see. Okay, and then another paper was by Frank Tipler, who did a paper on negative cosmological constant. So what he did was take the cosmological constant and take it over to the matter side. So it was like a property of matter itself, and did work on what would happen if you have a negative cosmological constant. You get singularities at the beginning and the end coming out of this system. Now, if you do that, what? Oops. You can imagine then that the arrow of time on our electrons is reversed to the arrow of time on positrons. The cosmological constant in terms of electrons is this positive force that accelerates everything. It's called dark energy. But if you had, if positrons are fully time reversed and the cosmological constant on them is reversed, you would have a negative cosmological constant effectively on antimatter. So at the primordial quark gluon soup, you would have positive cosmological constant on matter and negative cosmological constant on antimatter, collapsing it into these primordial black holes, which then would complete the loop, and the universe would spring into being, and it would solve the antimatter. Where's the antimatter problem? Because you've got all the antimatter has gone into, or enough antimatter has gone into these black holes. You would still get some stars collapsing as black holes as well, but we've got 80% of the mass in the universe is dark matter. So it could easily be that, well, it could possibly be that the missing antimatter is in these primordial black holes. So you've got the idea of some kind of reversed arrow of time on this inverted matter, similar to what happens in the movie Tenet. Okay, so we're left with the beginning matching up with the ending. So it's almost like the universe itself creates itself. So you've got this principle rather than the multiverse, which we don't know how to compute the probability of our existence. Sort of anything that can exist exists. What if the things that exist are the ones that are self-consistent, that if they did exist, they would create themselves? So that principle of if it did exist in the multiverse, it would create itself. That feedback loop could basically overcome the infinite possibilities that would just cancel each other out. And I think I will stop there for some questions. Okay. First question was sent to me from Nigel Hughes, who's a Pauline from 1951 to 1956. Thank you, Nigel, for your question. So timing the Big Bang as time equals zero. Theoretical physicists seem to have a fair idea of what was going on at time zero onwards, zero plus, where the plus is very small. So that's all physics. What happened at time equals zero? To start it all was described to me by an astrophysicist as metaphysics. What happens when you set the Tardis wheels to zero? Okay, so you go right back to the beginning. An impossible philosophical question, perhaps. What was there before time equals zero? In a sense, it is metaphysics, and we can never know, but there are some very interesting ideas that flow on from our physics, and the mathematics can take us further. One of the ideas that really caught my imagination about the beginning point was Roger Penrose's recent idea about CCC, conformal cyclical cosmology. So he imagines the universe going back and back and back, and as you get to the point where you get to the beginning, you get increase in energy to the point where you would have a unification of the forces, and all you would have would be massless particles, like the photon. Everything would be unified with the photon. The energy is too high for anything to actually have mass, and you just have photons on that initial state. Now, what he says about that is that the idea of time, when you don't have any mass, fundamentally breaks down. So to have a clock, you need both a mass, and then you can have something oscillating. If you've got something that's massless, it doesn't experience time. So if you've a photon, time does not happen on a photon, if you like. It's in a sense, frozen in space. So beyond that point where your Tardis would go, so Tardis would get back to the initial point of the existence of matter, but beyond that, you would have like an infinite regress of that information going on and on into the past, like an ordered series of events, but you wouldn't have time. The universe would have effectively forgotten about its time scale, and that information processing could effectively be infinite, that always existed. So it almost like the matter in existence comes out of the light eternal that goes back. Roger Penrose imagines that you could have effectively an infinite sequence of universes happening at different aeons, he calls them, and in a backwards sequence. But that again is metaphysics. But before time zero, so if time zero that your TARDIS could get to would be the starting point of the existence of matter. Beyond that, you've got an infinite sequence of massless information that is timeless, and the universe would spring out of, or the matter in the universe would, that starting point would spring out of that. A bit like the particle creation. So where is it? So pair production. So you've got all the information in the light, which is timeless, creating this matter, the antimatter and matter, which then forms the universe and the Big Bang. Okay, let's see the other questions. How do I see the questions? Is the accretion disk a sphere around a black hole? No, the accretion disk around a black hole is a disk. So the appearance of the curve on the top and the curve on the bottom is just entirely due to the light being bent. So it's like an optical illusion. So if you went around the other side of the black hole, you would see a disk. It's just because you've got the black hole in between you and that part of the disk that light would be curved, and you get reflections of that it appears spherical. So the disk is just a circular. How many times bigger is a black hole than the Earth? Well, for a black hole that's formed from a star, you need something that is maybe 10 times the mass of the sun. But for a primordial black hole, they could be less than the mass of the, a lot less than the mass of the Earth. If they're too small, they wouldn't have survived to 13.7 billion years. They would have evaporated by now. So there's a minimum size that they would need to be above, about the size of an asteroid. And the planet 9 could be a black hole, potentially, and its mass would be about 5 times the mass of the Earth. What else have we got? What happens if a positron escapes a black hole as Hawking radiation? How will it interact with regular matter nearby? Yep. So you can imagine that this is the inverted matter streaming out into the universe. So all this inverted matter would stream out, and then it would annihilate with matter, and that light would go forward in time. So it would just like the particles would disappear. You've got a negative lepton and a positive lepton. They disappear. There's no leptons. You've conserved lepton number, and it goes light into the future. So you could imagine that the end point, when every primordial black hole evaporates and all the antimatter comes out, you would have a firestorm where all the elements would be destroyed in fire, and going forward you would have just light. So again, it would be like the ending in Roger Penrose's cyclical cosmological conformal cyclical cosmological system, where the eons into the future, where you just have light, there's no mass anymore. Therefore, the universe has forgotten scale, and effectively you've got the same setup as you had at the beginning. So the end is like the beginning in that sense. Why does a merged black hole have less mass than some of the mass of merging black holes? Okay, so a lot of the energy when you have black holes collide will actually be in the rotation. It's almost impossible to fire black holes directly onto each other, and as they approach each other, they start spinning more and more rapidly in space-time. And what this does is creates massive waves in space-time which take this energy. So you would have energy transmitted not through light but through space-time itself, and that radiates through the universe. That's what we would detect at the LIGO experiments, for instance. That energy then stretches and pulls the whole universe around it, and even millions of light years away we can measure that stretch and pull as those waves pass through it. That has energy. Yuki, hi Yuki. Is there a determined rate of evaporation for black holes, a determined time when it begins after the black hole is created? Yes, so the time for evaporation is very much dependent on the mass of a black hole. The larger a black hole, the longer that time is, sometimes imaginably longer. If you've got a very small black hole, and some of these primordial black holes may have been quite small, then they will evaporate much faster. And what happens is, as you evaporate, you get smaller, and then the rate of evaporation happens faster. So the Planet 9's black hole, if it's a black hole, being 5 times the mass of the Earth, would have a surface temperature much less than the background radiation, the microwave background. So it's not even, if it was a black hole, it wouldn't even be able to radiate until the background is, it wouldn't even lose mass until the background is colder than it is. But eventually, with the expansion of the universe, it will be colder than even the surface of the supermassive black holes. But for smaller black holes, they're potentially have a surface that's hotter than the current microwave background, and as they radiate, they'll get smaller, and then they'll radiate more and more, and eventually there's a runaway effect, and they will explode in a blast of energy. It is possible that some of the extreme cosmic ray detections have been, it's been hypothesized that that is that effect. And let's take one more question. Is there a specific element that a black hole consists of? And what state of matter is it? Okay, so it's very hard to tell what's in a black hole until it passes that page time. So if there's not any information coming out, it's just going in, the black hole's getting bigger. It will look the same whether you throw antimatter or light or normal matter, anything, it'll look the same on the outside. But eventually it's now thought that that information of what went in will come out. And then after it hits that halfway point of being, so it's evaporated halfway, then that accelerates and information just keeps on coming out. Okay, well, let's answer a couple more. How do the wormholes stay open if exotic matter repels anything? None of this depends on exotic matter. Okay, so this was only, so there may be exotic matter and there may be ways to make the wormholes bigger, but this was just ideas looking at the information transfer with the laws of particle physics and the particles that we know of. We might be able to, well, it might be physically possible within those bounds. And last one, if we manage to travel faster than the speed of light, can we go forwards or backwards in time? I don't think the laws of physics, as we understand them, forbids travel of matter faster than the speed of light. It doesn't stop things that are already faster than the speed of light staying faster than the speed of light. And there is hints at non-locality and non-local information flow in general relativity and in quantum mechanics. So there's a possibility for that information to flow, but not objects. Objects you would have to destroy completely to reconstitute somewhere else. Okay, I think I will end there. Thank you very much, and I'll pass it back to Sarah.